Hi everyone, I am Santhi from Department of Mathematics and Statistics, Vivekananda College, and I am here with lesson 8 from linear algebra on vector spaces. In this lesson, I am going to explain about subspace of a vector space, its definition and examples. What is subspace of a vector space? For this, let me take a vector space like this as a set, because every vector space is a set first. Then suppose it has a subset H1 and it has another subset also H2 and it has another subset H3. So if it has like this many subsets, then are all these subsets form subspaces for this vector space V? Need not be. For this, let us recollect. In group theory, we have learned if G is a group, any non-empty subset H of G is said to be a subgroup of G if this H forms a group on its own with the same operations defined in G. The same way, if you take a ring R, then any non-empty subset S of R is said to be a subring of R if this S forms a ring on its own with the same operations defined in R. The same way, take a field and its subfield S. All these will form subring or subgroup or subfield if the subset itself on its own forms a group or ring or field with the same operations defined in the parent group or ring or field. The same way for the vector space V, suppose if I have a subset H, non-empty subset H, when will it be a subspace of V? If H forms a vector space on its own with the same operations defined in V. Here comes the definition of subspace of a vector space. Let V be a vector space. Any non-empty subset H of V is said to be a subspace of V if H itself forms a vector space with respect to the same operations, that is vector addition and scalar multiplication, which are defined in V. That means, so if I am given a vector space V and then I am given with a set H. If I have to prove that this H is a subspace, I have to prove all the 10 conditions again, because the definition said that H will be a subspace of V if H itself forms a vector space with respect to the same operations defined in V. That means in the definition you have all 10 conditions, but proving again 10 conditions, it will be lengthy. Instead that we have further one more definition for the subspace of a vector space. That is, a subspace of a vector space V is a subset H of V which has the following properties. Here we are giving only 3 properties. What is the first one? The zero vector of V is in H. What do you mean by that? Suppose in V I have 0, for example. Suppose V is R3 and I have, what is the 0 vector in R3? We all know that is 0, 0, 0. So this should be again 0 vector in H also. That means H cannot have one more 0 vector. Whatever the 0 vector is there in V, that will be 0 vector even in H. That is the first one. And the second one, H is closed under vector addition. That is U plus V belong to H for all U comma V belong to H. This is the required in the definition of vector space. That is, sum of any two vectors is again a vector. So what is the next one you have here? H is closed under scalar multiplication. That is, CU belong to H for all U belong to H and C is any scalar. This is again scalar multiplication, which is already defined in the vector space definition. So instead proving all the 10 conditions in the definition of vector space, if any non-empty subset H satisfies just 3 conditions, these 3 conditions, then it will form a subspace for the given vector space. Now let us see few examples how to show a given set is a subspace of a given vector space. So here we are having H is equal to set containing ST0, a column vector ST0 where S comma T belong to R. This is a subset of R3. We know R3 vector space, which has all the 3 tuples, or a column vector with 3 rows, and you have to show that it is a subspace of R3. Now we will just prove the 3 conditions. What are those 3 conditions? First one is regarding 0 vector. Second one is sum of the 2 vectors is again in H. And the third one is Cu belong to H. These 3 conditions are enough to prove that it is a subspace of R3. So I'll see the first condition. So 0, what is that? 0 vector in V. So what is 0 vector in R3? 0 in R3 is 0, 0, 0. Then it will be there in H also, because what is H having? H should have a vectors of the form ST0 where S and T are real numbers. So here this 0 and 0 are real numbers. In place of S and T you have 0, 0. So this will be there in H such that 0 plus U is equal to U plus 0 is equal to U for all U belong to H. So the first condition, that 0 vector in R3 is also a 0 vector in H. The first condition is satisfied. Then what is the second condition? Second condition is U plus V belong to H. So I'll take U is equal to S1 T1 0. V is equal to S2 T2 0. So the same type of elements which should be there in H. What is the condition? The third row element should be 0. So let me take belong to H. What will be U plus V? So how do you add these two? S1 plus S2, T1 plus T2, 0 plus 0. So which is equal to, in the form S1 plus S2, T1 plus T2, 0. It will be there in H. Why? What is the condition to be in H? The first two elements and the last third row element should be 0. And the first row element and the second row element, these two should be S1 plus S2 and T1 plus T2 belong to R. Why? Because S1 belong to R, S2 belong to R. T1 belong to R, T2 belong to R. So their sum will be also there in H. Therefore, U plus V belong to H. So the second one is over. And the third one, Cu. So what is C into U? Already U have taken as S1, T1, 0. So this will be, we know how to multiply a scalar with a vector, with a matrix, column matrix you can say. So this will be there in H. Why? Because CS1, C T1 belong to R. So we proved the 3 conditions which are required for H to be a subspace. So H, therefore H is a subspace of R3. Our second example. Can the vector space R2 be a subspace of R3? Usually we'll feel that R2, R3. So R2 is a 2-dimensional plane, like geometrically, and R3 is a 3-dimensional plane. We'll assume that this R2 will be part of R3 usually. Each plane is a part of some space, that is true. But algebraically, let us see whether it forms a subspace or not. So let me write what is R2. R2 has all the vectors of the form AB such that A comma B belong to R. Then what is R2? R3 having? R3 has, I'll just change the name of the vector ABC such that ABC belong to R. So before proving a subspace, first if you observe the definition of subspace, whatever H if you want to prove as subspace, it should be a subset first. Can I say R2 a subset of R3? If I take U is AB, it does not belong to R3 first. That means any element in R2 cannot be in R3 algebraically, which implies R2 is not a subset of R3. If it is not a subset, it cannot be a subspace. Because before proving the conditions, first of all, the given set should be a subset of R3. If it is not a subset, there is no question about subspace. Our next example. H is the set of all polynomials P of t in Pn such that P of 0 is equal to 0. Can H be a subspace of Pn? So, solution. Before solving this, I want to just give you what do you mean by P of 0 is 0. That means if I take P of t as a0 plus a1t plus and so on an t power n, then what do you mean by P of 0? Wherever you have t, you should substitute 0. a1 into 0 plus and so on plus an into 0 power n. So this is nothing but just a0 is equal to 0. What do you mean by that? a0 is 0. That means it will have all the polynomials in which constant is 0. Just as an idea before doing this. Now let me write what is H having. H has all the polynomials which belong to Pn such that P of t, P of 0 is equal to 0. So if you take this, it will be obviously a subset of Pn. Why? Because you are taking all the polynomials from Pn only. So H will be a subset first. Not like in the previous example, we got R2 is not a subset of R3. But here, H is a subset of Pn. So let us go by point first one. What is the first point? The first point is 0 element in Pn. That should be 0 element even in H. So what is 0 element in Pn? 0 in Pn is 0 plus 0 into t plus and so on plus 0 into t power n. So if I take this as, like I'll denote it as O of t, suppose. Then it should be there in H means what should it satisfy the condition? P of 0, 0 means, so we have to have O of 0. What is O of 0 then? 0 plus 0 into 0 plus and so on plus 0 into 0 power n is 0, which implies this 0 polynomial or O of t. It is there in O of t. I can say O of t is nothing but 0 belong to H. So whatever the 0 polynomial in Pn, it is there in H, the first condition. The second one, sum of two polynomials. So I will take P of t plus Q of t. I have to prove that. So to prove that P of t plus Q of t belong to H. Now when will this be there in H? If you put t is equal to 0 in this, that should give you value 0. So consider P of 0 plus Q of 0 is equal to. We know P of 0 is 0 and Q of 0 is 0. so which will be 0, so it is there in H. That is the second condition. Therefore, P of t plus Q of t belong to H. Then what is the third one? C into P of t. You have to prove that C into P of t belong to H. So for this, consider C into P of 0 is equal to, what is C into, already P of 0 is 0, is 0. That implies C into P of t belong to H. Therefore, you have C into P of t belong to H. By all the three conditions, this H forms a subspace of Pn. Our next example is also in polynomials. Determine whether the set of all polynomials of the form P of t is equal to a plus t square, where a belongs to R, forms a subspace in Pn. So let us see the solution. So what is the subset here? It is H. It has all the polynomials which are in the form a plus t square such that a belongs to R. Now first of all, whether H, is it a subset of Pn or not? Yes, it will be a subset of Pn. Why? Because Pn has all the polynomials up to nth degree, maximum nth degree. That means it will have 0 polynomial, first degree polynomial, second degree, and up to nth degree, whatever n you take it. Now here I have taken, it is a second degree polynomial, a plus t square. So it will be there, it is a subset of Pn. So we'll see the first point. What is 0 in Pn? So 0 in Pn, simply I can say, though it is a 0 polynomial like 0 plus 0 into t plus 0 into t square plus and so on plus 0 into t power n, it is nothing but 0 only, right? So if this 0 in Pn should be there in H, then if this 0 belong to H implies this should be equal to, it should be in what format? In the format a plus t square. What do you mean by that? The constant, so implies I should have a is 0 and another one. There is no t term, okay, t coefficient 0, okay, fine. Then t square coefficient, here I have 0, but I have here t square coefficient as 1. So I must have 0 is equal to 1, which is not possible. That therefore, 0 element in Pn is not in H. Now can it be a subspace then? No. Therefore, H cannot be a subspace of Pn. Why? Because the 0 element itself is not existing in H. We don't need to check the other two conditions. Last example I'm going to give here is a plane which does not pass through origin is in R3. Does it form a subspace of R3? So the given vector space is R3. Before doing it algebraically, let us look at it graphically, or I can say geometrically. So I am taking R3. What is the given vector space to us? R3, which is a three-dimensional. So this is R3. So this is origin, which you can call it as even 0 vector here. This is x, y, and then z. This is R3. Now there is a plane which does not pass through origin. In three-dimensional space, you will have infinitely many planes like one plane, this is one plane and this is another plane, and I have one more plane like this. Some planes will be lying in xz plane, some planes will be lying in only in yz plane or only in xy plane. Some planes will be passing through all the three planes. Some planes will be passing through origin, some planes will not pass through origin. There will be infinitely many planes in this R3. Now what is our question? A plane which does not pass through origin. Suppose I have taken a plane which does not pass through origin. Can it be a subspace of R3? What is origin actually for R3? Origin is nothing but zero element. Zero element in R3. Now this 0 does not belong to our H here. What is H? It is a plane does not pass through origin. Now 0 does not belong to H, then it cannot be a subspace because 0 element in R3 must be there in H. Therefore, H is not a subspace of R3. Here comes the last point in our lesson. A given vector space can have many subspaces, can have few subspaces, may not have any proper subspaces, but obviously it must be having minimum two subspaces. That's what here I have given. For any vector space V, there always exists minimum two subspaces. What are those? First one is H is set containing 0. That means any subset which has only 0 vector, it will be always forming a subspace, which we call it as trivial subspace. And the vector space V itself is a subspace of V. For any vector space, the vector space itself forms a subspace which you call it as improper subspace. So this you call it as improper, and this set containing 0 you call it as trivial. So for any vector space there will always exist minimum two subspaces. If there exists any other than these two, they are called as non-trivial proper subspaces. Other than the above two. Other than the above two, if the vector space has any other subspaces, you call them as non-trivial proper subspaces. We have a theorem on subspaces, that is, prove that the intersection of two subspaces is again a subspace. Or if H and K are any two subspaces of a vector space V, then H intersection K is also a subspace of V. Let us see the proof. So what is given here? Let H and K be any two subspaces of a vector space V. Then H intersection K, what will it be? It is having U belong to V such that U belong to both H and also U belong to K. This is the definition for the intersection of two sets. Now you have to prove that H intersection K is also a subspace of V. So for subspace, what are the points we have to prove? There are 3 points we have been proving in the previous problems for any subset to be a subspace. First one, 0 in the vector space V is also there in the whatever the set, we have to prove it as a subspace. And next one is U plus V, any sum of any two vectors should be there in that H, and the multiplication of a vector with a scalar also should be there in H. These 3 points we have to prove. Now let us prove these 3 points for H intersection K. H intersection K is a subset of V because both H and K are subsets of V. So you have H intersection K also will be a subset of V. Now the first one, let 0 be the 0 vector in V. Then implies 0 will be there in H and also 0 belongs to K. Why? Because H and K are subspaces. The 0 vector in V must be the 0 vector in H and K or in any other subspaces. That implies you can say 0 belong to H intersection K because it is there in both H and K. It will be there in H intersection K also. Second point, let U comma V belong to H intersection K. Implies U comma V will be there in H as well as U comma V belong to K also. Implies if U and V are there in H, since H is a subspace, so what can we write? U plus V will be there in H and also U plus V will be there in K because both H and K are subspaces. H and K are subspaces of V. Sum of any two vectors should be there again in the same subspace, which implies U plus V belong to H intersection K. That is the second point we have to prove. Now let us see the third one. Let U belong to H intersection K and C be any scalar. Implies we have U belong to H and U belong to K, comma C be any scalar. That implies U belong to H, C be any scalar as well as U belong to K and C be any scalar. Now again here H and K both are subspaces, so we can say CU belong to H and CU belong to K. That implies why? What is the reason? Since H and K are subspaces of V. The same reason you have been applying in all the points. This implies you can say this CU which is there in both H and K, so you can say that CU belong to H intersection K. Therefore, by all the above 3 points, whatever we have proved here, H intersection K forms a subspace of V. So let us give a note point here. That if H1, H2 and so on, Hn are n subspaces of a vector space V, then their arbitrary intersection H1 intersection, H2 intersection and so on, Hn is also a subspace because intersection of two subspaces is a subspace. Similarly, intersection of 3 subspaces, intersection of 5 or 10, like that, intersection of n number of subspaces will be also a subspace in V. Now we have seen the intersection of two subspaces. What about union of two subspaces. So suppose I have a vector space V and there are two subspaces H and K. Let me take like this. This is V and this is H, and then I have another subspace K. Then H union K, will it be a subspace of V or not? Need not be always. So under what conditions H union K will be a subspace? H union K will be a subspace of V if and only if either H is a subset of K or K is a subset of H. Only under this condition, their union will be again a subspace. That is, if you take V like this, you should have, if this is H, then that should be K. That is, K is a subset of H, or if this is V and the subspace K is this, then H should be a subspace of K. That is what, either H is a subspace, that is subset of K, or K is a subset of H. This is what the theorem says. The union of two subspaces need not be always a subspace, only if and only if either H is a subset of K or K is a subset of H.